Hello, this is Return. I'm really glad to share our paper, Aggregated Residual Extended Time Delay Neural Networks for Speaker Verification. The motivation of this paper is to build ideal speaker verification networks that will capture time sequential information and extract the deep representation of speakers. The outline of our presentation is as follows. First, we will talk about the background of this paper. Then, we will introduce the proposed model. Third, we will illustrate the experimental setup of our work. Then, we will display the experimental result of the proposed model. And the last part is our conclusion. Speaker verification is an open side recognition problem. An utterance is verified to be a certain speaker if their similarity exceeds a threshold. Figure 1 shows a diagram of the speaker verification system. Currently, end-to-end speaker verification utilizes neural networks as a feature extractor to extract robust embeddings in complex scenarios. The mainstream end-to-end speaker verification models are time delay neural network and ResNet. Figure 1 shows the structure of X-vector system, and this figure illustrates the architecture of deep speaker. Although time delay neural network and ResNet both achieve the satisfactory performances in speaker verification, they even have some disadvantages. Time delay neural network approaches will capture time sequential information, but they lack the delicate transformations needed for deep representation. ResNet extracts high-dimensional representations feature of speakers, but specialized convolution kernel does not process feature by considering complete dimensions of frequency. A commonly used structure of time delay neural network is illustrated in this table. Comparing the architecture with a very deep convolutional network with hundreds of layers, we can see that the time delay neural network for speaker verification is indeed too simple. This is a spectrogram. The red box means the 3 times 3 convolution kernel. We can see that in the process of one convolutional neural network layer, the convolution kernel does not consider complete dimensions of frequency, but speech signal of each frequency carries the personal characteristic of the speaker. So we believe that convolutional neural network may be not very suitable for speech verification, and at present, convolutional neural network has a relatively good effect on speaker verification tasks, mainly due to the strong representation of speakers of very deep ResNet. The objectives of this paper are as follows. We believe that ideal speaker verification networks should combine the merits of time delay neural network and ResNet, which can model long-term temporary dependencies of speech and extract a deep representation of features. Robust speaker verification networks should adopt a delicate strategy to extract more discriminative representation and build more efficient models. This paper adopts the split transform merge strategy and shortcut connection in time delay neural network to build aggregate residual time delay neural network blocks. The proposed model uses the aggregate residual time delay neural network blocks to replace the extended time delay neural network layer in the extended time delay neural network. In the time delay neural network layer with the split transform merge treated. The input feature is split into C subfeatures, which are passed on to corresponding sub-time delay neural network layers with same topologies. Each sub-outputs are concatenated as the output of the transformations. The aggregate transformations in time delay neural network can be presented as this formula. In the formula, T sub xi is the S sub time delay neural network nano, and C is the size of the set of transformations to be aggregated. This picture shows that a time delay neural network layer with aggregate transformations only have one set of the parameters of the convolutional time delay neural network. Then we introduce residual transformations in time delay neural network, and aggregate transformations in TDN can be combined with the residual transformations and defined as this formula. X is the input feature and Y is the output of the network. In this paper, the aggregated transformations in TDN combined with the residual transformations are used to build our aggregate residual time delay neural network blocks. This picture is the architecture of an aggregate residual time delay neural network block. C is the number of sub time delay neural network layers. This table shows architectures for time delay neural network, extended time delay neural network, residual extended time delay neural network, and aggregate residual extended time delay neural network. T is the number of training segment frames, and N is the number of speakers. To facilitate comparison, we set N to 1000 for every network. The first part of the table is conventional time delay neural network. This is the extended time delay neural network. It inserts a dense layer between two time delay neural network layers. The third part is residual extended time delay neural network. It uses TDN blocks with residual transformations to replace the extended layer in eTDN. This part is the aggregate residual extended time delay neural networks. ARET utilizes residual transformations and a split transform merge treated to build an extended time delay neural network layers. Compared to RET, ARET significantly reduces the parameters and flop point operations and has more delicate representations for speakers. We adopt the additive angular margin softmax loss as a loss function of our proposed models. The AAM softmax can increase the inter-speaker difference and reduce the intra-speaker variation by introducing an additive angular margin in the softmax loss. The additively angular margin softmax loss can be described as this formula. N is the number of train samples, C is the numbers of speakers in the train site, and M is the additive angular margin, and S is the scaling factor. The details of our experiments are as follows. The development set of Voxlab 2 was used to train our models. We evaluated models on the test set of Voxlab 1, Voxlab 1e, and Voxlab 1h. The equal error rate minimum detection cost function from NIST SRE8 and SRE10 was selected as the performance metrics. We use the well-trained X-vector models as the solid baseline. We adopt the time-delay neural network and additive angular margin softmax loss to build our X-vector model. 161-dimensional spectrograms as the input feature for our models. In AAM softmax loss function, the margin M and scalar factor S was set to 0.25 and 30, respectively, and the C in ARET was set to 32. This table shows the configuration of databases under our experiments. To prove the validity of proposed models, we adopt 3 evaluation sets of the test sets of work-soluble 1, work-soluble 1E, and work-soluble 1H. The trial of work-soluble 1E and work-soluble 1H include more than 500,000 pairs of utterances. This table shows the experimental results of our paper. From the table, we can see that ARET has a great performance improvement over time-delay neural network and ResNet. The present ARET achieved state-of-the-art performance with 1.389% equal error rate on the work-soluble 1 test part, compared with the best baseline in this part. ARET had a 32% relative decrease. On work-soluble 1E and work-soluble 1H decreased the equal error rate to 1.520% and 2.614%, respectively, which are both 45 relatively lower than the best results in a strong baseline. This is the DET curve of experimental models. We can intuitively see the improvement of performance for the proposed model. This paper presents 2 strategies to replace ResNet and the time-delay neural network as a feature extractor in the end-to-end based speak verification. The proposed models can consider time sequential information and have an efficiency deep representation needed for speak verification. The highlights of the proposed model are as follows. Experiments on work-soluble datasets without any augmentation indicate that the best proposed ARET realizes satisfactory performance on the work-soluble 1 test set, work-soluble 1E, and work-soluble 1H with 1.389%, 1.520%, and 2.614% equal error rate respectively, compared to state-of-the-art results on this test set. ARET achieves a 32% to 45% relative reduction in equal error rate. Thanks for your listening. If you are interested, please look for our full paper. Thank you.